Good afternoon everybody. Today I am going to take the class which is for the 5th semester, and subject is introductory econometrics, which is in your 5th semester, and core course 11. Okay. So, I will take the class linear regression. So, first of all, what is the definition of regression? Regression analysis is a statistical technique for investigating and modeling the relationship between variables. Okay. So, you have heard about regression and you have known the methods of regression in your statistics paper, but here I would like to teach you the regression of econometrics. So, the econometric regression has a vast application. So, it is applied in almost every field nowadays, including engineering and physical and chemical sciences, and of course, in economics, in management, in life and biological sciences, and in all kinds of social sciences like history, education, etc. So, it is the widely used technique to understand the relationship between different variables and also to predict the relationship in future, which is immensely helpful for policy purposes, not only in case of economic policies, but also in all kinds of policies in almost every subject. So, but then regression in statistics and regression in econometrics are two different concepts which I would like to elaborate a bit. Now, suppose that we are talking about the relationship, economic relationship. Suppose we know that consumption depends upon income. As income increases, consumption increases. This relationship we learn from the economic theory. Now, how far it is empirically applicable? So, does that happen in real life always? In order to find out that, we have to construct the regression between consumption and income. Now, the difference between statistics and econometrics is that in case of statistics, suppose we are talking about the linear regression, then we can form one regression relationship by the equation of a straight line, which looks like this. Now, we know that consumption is a function of income. Now, we are trying to find out the relationship between consumption and income by constructing one linear regression equation and then solving it. So, we can write C equal to alpha plus beta y, beta y. Now, we can have a number of observations of income and consumption, and statistically we can solve them, and then we can find out the values of alpha and beta from here, which would be the unique values. That means, there will be only one value of alpha and only one value of beta after solving this regression equation, and this you know from your statistics chapter of linear regression. But what is different in case of econometrics is that in our real life, everything is not so much clear and free of errors. There are some uncertainties in our life. So, due to that uncertainties, we do not have the unique result of our equation. Suppose that all persons are getting education, but not all persons are getting equal employment opportunities. Suppose two persons have similar similar educational qualification, but they are not getting similar jobs with similar wages. Now, why such difference happens? Because of the uncertainties in the real world. Now, these uncertainties can be explained in a lot of ways. That means there are many other variables that are explaining the job opportunities, getting jobs. Now, we are not incorporating them, we are only getting the information of education. So, that creates imperfectness, and there are some human errors also. So, the results are not unique like the case of statistical regression equation. Now, statistical regression equation is almost like a laboratory experiment. In case of laboratory experiment, we create the ideal atmosphere, we control all the other variables, and then we see the result. Here, in case of statistical regression equation, this thing is happening. But in case of econometrics, there is a scope of uncertainty. Now, since we incorporate that uncertainty and we have to find out the solution for the real world problems where we face the uncertainties everywhere, econometrics is so much important in these years. So, let us go to an example to show how the uncertainties are entering into our problem. Suppose we have a data of price and length of 74 cars. We assume that the price, now we all know that the price of the car increases with the increase in the length of the car. The bigger the car is, the higher will be the price, everybody can say that. Now, whether this relationship is applicable for everywhere, for every country, for every place, whether that relationship can be said within an wink of eye. So, for that purpose we have to examine the relationship, and so we get our 74 observations. Now, in the horizontal axis we plot all the values of our 74 values of length, and in the vertical axis the corresponding prices are plotted, and all these combinations, the points, these points of the combinations are plotted in a graph which you all know is called the scatter diagram. Now, this is the scatter diagram which we have constructed from that 74 observations. Now, what is the first impression from this scatter diagram? That we can say that it is loosely upward rising. That means as length of the car increases, price of the car also increases, but it is not the exact positive relationship. It suggests that there might be the positive relationship between the price and the length of the car, but it does not fall on the same straight line. All the points do not fall on the same straight line. But if we construct a regression equation like this, y equal to beta 0 plus beta 1 x. Now, here the relationship, in this relationship, y represents price and x represents length. Then the equation will be y equal to beta 0 plus beta 1 into x. Here beta 0 is the intercept of the line and beta 1 is the slope of the line. As you all know that if I draw one line, here it is the y axis and here it is the x axis. Now, if the line is like this, then the distance covered in the vertical axis, this is called intercept. And if the line is standing on an angle theta with the horizontal axis, then tan theta will be the slope, or it is the perpendicular by base. Everybody knows that from the trigonometry which we have learned during our class 10 mathematics. So, here we constructed this equation where beta 0 is the intercept and beta 1 is the slope. Now, if we plot now we are getting from this equation different expected values of y for given values of x. So, we are getting the expected values of y, which is the mean values of y for different values of x, and here we have 74 values of x, which is 74 values of length. So, say for 74 different values of length, solving this equation we are getting expected values of y, that is expected values of price, which is the mean value. Now, if we plot those values, only those mean values in the diagram, same diagram, and then we just join them, then we are getting the blue straight line, which is upward rising. Now, in the same straight line, in the same diagram, scatter diagram, we are getting some red actual points of prices and the mean values or expected values of the prices that are represented in the blue straight line. Now, obviously, we have seen that all points do not fall on the straight line. So, some points actually are away from the straight line. So, there is some error. That is the thing which I was discussing about, is that when we are taking the real life prices of the cars according to on the basis of their lengths, we are not getting the ideal mean values or expected values. We are getting the actual values which are different from the expected values. The expected values only lie on the blue straight line. So, actual values are away from the straight line, that is expected values. So, this distance, each of the point is lying either upward or downward from the straight line. So, this discrepancy can be called error. Now, what will be the error? Where will be that red point? We do not know that. That is why it is completely random, it is beyond our control. We do not know how much there will be difference between the actual value and the expected value of the price of the car. So, to make the model more perfect, we should incorporate this error. Otherwise, this will be like a laboratory experiment which we do generally in the regression of which we have learned in statistics. So, we have to incorporate this error, and this error is perfectly random error. Okay. So, there is that difference between the regression line, straight line of the linear regression in statistics and in econometrics. Now, this equation 2 is the linear regression line which we use in econometrics, and the difference is that incorporation of the term epsilon, which denotes the random error that is present in our everyday life. So, therefore, this model explained by the equation 2 is called the linear regression model. Now, y is called the regressand or dependent variable. So, it depends upon the x or regressor or independent variable. So, independent variable is given exogenously, we cannot control it. But we are trying to find out how y is depending upon x. So, y is the dependent variable or regressand whose value we are trying to find out from this regression. Now, since there is only one x or only one independent variable in our model, so this is called the simple linear regression model. Now, in the real life, as we have already mentioned, that there are many explanatory variables to explain one certain variable. So, to explain the price of the car, there might be a number of explanatory variables that we are not considering here. We are only considering the length of the car, whether the car is big or not. That is only one variable. So, therefore, if we could incorporate all those variables, then the equation would look like equation 3. Y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus dot 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 plus beta k xk plus epsilon. Suppose we are having k number of regressors or k number of independent variables. So, if we could incorporate all of them, then this model would be called multiple linear regression model, since there are multiple independent variables here. Now, x is fixed. In our regression equation, x is given, x is exogenously given, x is the independent variable. So, therefore, in our regression equation, we are trying to find out x on the basis of trying to find out the values of y on the basis of x. Okay. So, x is perfectly given, x is exogenous. So, we are not bothered by x, we are bothered by the error term. That is the main problem in our equation. Now, whenever we are trying to find out the values of y, remember, whenever we are trying to find out the distribution of a certain variable, we would like to know two things. One thing is the central tendency of that variable, that is how it is centered and which is mainly measured by the mean value, and how the different values are away from that central value, that we measure by the variance. So, therefore, to find out to know about the distribution of any variable, we would like to find out the mean and the variance of that variable. That is the two things of our concern. So, therefore, obviously, we would like to find out the mean value and variance of y. Now, here the mean value is called conditional mean. That means, given certain values of x, what will be the expected or mean value of y. That is why it is written like expected value of y given x, which we denote by mu y given x. Now, x is given and we are trying to find out the mean values. That is expected value of, now put the value of right hand side of the equation in it, beta 0 plus beta 1 x plus epsilon. Now, in case of expected value, in case of the mean value, we all know that the point will lie on the blue straight line. So, there will be no error. So, error will be 0. So, that is why it will be beta 0 plus beta 1 x. And what will be the variance of y? Since x does not pose any problem in our model, since x is given, so variance of y will solely depend upon the variance of the random error term. So, there is an intricate relationship between the variance of the error term and the variance of our dependent variable. So, since if we consider that the error term has a constant variance, that is sigma square, then variance of y given x, that will also be equal to sigma square. So, variance of x do not actually impose any problem on variance of y. Variance of y is solely determined by the variance of epsilon, that is error term. So, in the true regression model, that means on the blue line, blue straight line, the equation will be mu y given x equal to beta 0 plus beta x. That is, this is the line where we only have the mean values. So, therefore, the height of the regression line is just the for any value of x is just the expected value of y for that given x. That means, suppose we have constructed one regression line like this, y equal to beta 0 plus beta 1 x. This is the regression line, here there is no error term, and here this is y and here this is x. So, for each values of x, that is x1, x2, x3, the height is that y value, that is the mean value, expected value. This is the expected value. So, therefore, we are just getting the expected values from the regression line. Now, slope of the regression line, that is beta 1, which can be that this can be interpreted like del y del x, that is for 1 unit of change in x, how much unit of change will happen in y, that will be represented by beta 1. So, this is the marginal effect. Since we have constructed the linear regression model, that is why the solution is very easy. So, beta 1 is the marginal effect. So, beta 1 actually represents the change in mean value of y due to certain change in 1 unit change in the given value of x. So, that is the slope, and variability of y at a particular value of x is determined by the variance of the error component. Since this is the mean value will not be the actual value may vary from here to here. In each case, the actual value may vary from here to here. The actual values will be like this. And how much these actual values will be spreaded around the mean value? This will be same. This will be same because it depends upon the variance of the error, and since the variance of the error is considered to be constant sigma square, so variance of each of y value for a certain value of x will be the same, and that will also be sigma square. So, therefore, this error variance is determining the variance of y for each value of x. This implies that the distribution of y values at each x and the variance of this distribution, there is a distribution of y values at each x and variance of the distribution is same because that is equal to sigma square, because that depends only on the variance of the random error term. Now, how can we estimate the beta 0 and beta 1? We have constructed the equation. Now, we have to estimate the beta 0 and beta 1. Now, for this purpose, method of least squares, which is denoted as OLS, ordinary least square. This is denoted by OLS method, that is ordinary least square method. And least square method is used for estimating beta 0 and beta 1. That is, we estimate beta 0 and beta 1 so that the sum of the squares of the differences between the observations yi and the straight line is minimum. That means, the basic purpose of our model is to find out the relationship between y and x. If we know the exact relationship between y and x, then for certain values of x which we do not have right now, we can predict what will be the value of y. So, that is our purpose. Now, this x and y could be anything. So, in case of policy purposes, we can do that. Suppose we are trying to find out how much food rationing is needed for a particular group of people to lift them out of the poverty line. So, then if we can construct one regression relationship and if we find out the value of the beta 1, then we can easily frame that policy. So, that is why it is so much important. Now, we are actually estimating, we are not deducting. In case of mathematics or in case of statistics, we will call it determination or deduction, because the solution is unique, only one value will be there. But since there is a randomness in our model, we cannot find out the unique exact one value. So, we will find out certain probable values. Now, our purpose will be to set these probable values as close to the actual value as possible. If we can do that, then our whole exercise will be fruitful. Otherwise, if we cannot predict the close values, which will be actually very close to the actual value, then our model is futile, then our model is useless. Now, how can we estimate one model which will be close to the actual model? How can we estimate one model from where we can find out the values of beta 0 and beta 1 which will be very close to the actual beta 0 and beta 1? For that purpose, we have to rewrite the regression equation in sample regression format. What is sample regression format? That is, population regression is very difficult to do, because population data is very difficult to collect, it is expensive, it is time consuming. So, therefore, we find out the easiest method, that is to collect one sample which will be representative of the population, and then we regress that sample data set. Now, on the basis of that sample data set, we can rewrite the regression equation yi equal to beta 0 plus beta 1 xi plus epsilon I. Here the sample is finite, which is n number of samples, I equal to 1 to n. Okay. So, for this sample regression method, we will apply the same regression model as I have already discussed about, and we will find out the values of beta 0 and beta 1. Now, from one population n number of samples can be collected. So, therefore, n pairs of beta 0 and beta 1 can be solved out. For each sample, there will be one pair of beta 0 and beta 1. So, for n number of samples, there will be n pairs of beta 0 and beta 1. Now, our purpose will be to use a certain procedure from which we can find out the sample values of beta 0 and beta 1, that is very close to actual beta 0 and beta 1. That means, error is minimum. The distance between the regression line, blue line and the red dots should be minimum, and using the method through which we can get that is the least squares method. That means, we are actually minimizing the squares of the error terms. Now, we do not know the error term, this is the population error and this is absolutely random. So, what can we do? We can actually get the sample value of the residual, which can be considered as the proxy of the population error. That is, yi is the actual value of our curve price, and we fit a regression line. So, right hand side is beta 0 plus beta 1 xi, xi is the given values of length of the curves for n number of set. So, therefore, solving them we can therefore, deducting yi from deducting beta 0 plus beta 1 xi from yi, we can get the residual term. That means, actual value minus the expected value. So, that is none other than the residual or the sample value of the error term. But if we just sum up these errors and then minimize them, there is one problem. because there are some errors which are positive and there are some errors which are negative. So, if we add them up, they may actually delete each other and the result may be 0. So, therefore, we have found out a different process that we take the square of the errors, that is square of the residuals, and then sum them up and then minimize them. So, that is why we are actually minimizing the summation I equal to 1 to n yi minus beta 0 minus beta 1 xi whole square. This is the square of the sum of the squared residuals, which is shown by equation 4. Now, we have to minimize them with respect to beta 0 and beta 1 and set the first order condition as equal to 0, which is given by del s del beta 0 and del s del beta 1 in our slide, and which is equal to 0. So, these are, since these are given in summation terms, so these are the normal equations. To solve these normal equations, we use these equations, we can use the normal equations to solve them, and then after solving them we are getting the values of sample estimates. That is, these are the least square estimates of beta 0 and beta 1. So, we assume least square estimate of beta 0 is beta 0 hat and least square estimate of beta 1 is beta 1 hat. Beta 0 hat is equal to y bar minus beta 1 hat x bar, where y bar and x bar are the mean values of y and x, and beta 1 hat is equal to summation I equal to 1 to n yi xi minus summation I equal to 1 to n yi into summation I equal to 1 to n xi divided by n whole divided by summation I equal to 1 to n capital Xi square minus summation I equal to 1 to n capital Xi square by n. Now, this complicated term is the value of the beta 1 hat, which is represented by the equation 7. Now, beta 0 hat and beta 1 hat, these are the least square estimators as I have already mentioned. So, therefore, after fitting them, the equation looks like y equal to beta 0 hat plus beta 1 hat x. Now, there is no error term because this is the fitted line, this is the mean line, this is the regression line which is shown by the blue line in the diagram. So, in the equation 7, the right hand side was this, that is summation I equal to 1 to n yi xi minus summation I equal to 1 to n yi into summation I equal to 1 to n xi divided by n. If we solve them, we can get summation I equal to 1 to n xi minus x bar into yi, which is represented by n. Now, if anybody is interested how could we solve this equation, then you can contact me, I will show you, or it is given in the any textbook. And then denominator is summation I equal to 1 to n capital Xi minus summation I equal to 1 to n xi whole square divided by n. Once again, if we solve this will lead us to the solution summation I equal to 1 to n xi minus x bar whole square, x bar whole square. So, we denote Sxi is the as the numerator and Sxx as the denominator. So, a convenient way to write down the value of the beta 1 hat is equal to Sxy divided by Sxx, which is denoted by the equation 11. Now, difference between the observed value and the corresponding fitted value, as we have already known, is known as the residual. Now, ith residual is equal to Ei equal to, now since it is the sample error, that is residual, we are denoting it Ei. In case of population error, we would denote it as epsilon I. It is very important to remember all the notations because otherwise everything will be very ambiguous. So, Ei equal to yi minus y hat I, which is equal to yi minus within bracket beta 0 hat plus beta 1 hat xi. We are just putting the values from the equation 8. So, this looks like residual looks like this, ith residual looks like this. Now, what is the property of these two least square estimator? Now, I would mention just two properties here because there are more properties and certain properties will lead to us in the famous Gauss-Markov theorem, which I would discuss in the next class. I would just mention two properties, first two properties. First property is that beta 0 hat and beta 1 hat, they are the linear combinations of the observations yi. And as we have already known that beta 1 hat is equal to sxx by sxy, these can be represented by summation I equal to 1 to n small I yi, small ci yi. Here small ci is equal to small xi divided by summation small xi square. We have to remember that since now whatever equation I have used, x and y are given in the capital format, and if we deduct the mean value from the actual value, that is xi minus x bar, that will be denoted by small xi, and yi minus y bar will accordingly denoted by small yi. So, we have to remember the difference between capital Xi yi, capital X bar y bar and small xi yi and small x bar y bar, otherwise once again everything will be very ambiguous. So, therefore, we can easily solve this. We can assume that small xi equal to capital Xi minus capital X bar and small yi equal to capital yi minus capital Y bar, and then we have seen that actually beta 1 hat is the linear combination where the weight is Ci, summation Ci, here it is the weight, and so it is the linear combination. So, this is the first proof, and the second proof is that these least square estimators, that is beta 0 hat and beta 1 hat, are unbiased estimators of the model parameters beta 1 and beta 2. That means unbiased means expected value of beta 0 will be beta 0 hat, and expected value of beta 0 hat will be beta 0, and expected value of beta 1 hat will be beta 1. This is clear. Now, I have done the deduction for expected value of beta 1 hat, and I will ask you to solve the expected value of beta 0 hat at your home. So, how can I prove? I have taken expected value of beta 1 hat, which is equal to expected value of summation I equal to 1 to n Ci yi, as we have already known that we have taken it as assumption that beta 1 hat will be equal to summation I equal to 1 to n Ci yi. So, here since the Ci is the is certain weight and it depends only upon x, we have already seen that Ci depends only upon the small xi, that is capital Xi minus capital X bar, which is given. So, it is constant. So, that is why it is taken out, and then expected value of yi. Now, for yi we can put the value beta 0 plus beta 1 xi. So, if we break up, then we are getting beta 0 into summation I equal to 1 to n Ci plus beta 1 into summation I equal to 1 to n Ci xi. Now, summation Ci, what will be that? That will be equal to 0, because summation Ci means summation xi divided by xi square. Summation Ci means summation xi divided by summation xi square. That means summation xi square. Now, what is this? Summation xi minus x bar divided by summation xi square. This one is equal to 0, we all know that, because summation xi, that means n into x bar, and that means summation xi minus x bar, that is equal to summation xi minus summation x bar. Summation xi means n into x bar, or this is n into x bar. So, this is 0. So, summation Ci is equal to 0, and then summation Ci xi will be equal to 1. How can we prove that summation Ci xi will be equal to 1? Summation Ci xi, that will be equal to summation xi divided by summation xi square into summation xi. That means summation xi square divided by summation xi square, that is equal to 1. So, therefore, putting these values in this equation, we are getting beta 0 into 0 plus beta 1 into 1, that means equal to beta 1. So, we have proved that expected value of beta 1 hat will be equal to beta 1. Now, it is your task to prove that expected value of beta 0 hat will be equal to beta 0, and then we will move to the famous Gauss-Markov theorem in the next class. So, thank you very much.